Okay, great. Welcome everyone. And it's my great pleasure to welcome in particular Marco Bernardi to this seminar series, finally. So Marco received his PhD in material science from MIT, where he worked with Jeff Grossman on materials for solar energy conversion. And then afterwards, he was a postdoc in the physics department at UC Berkeley, working with Steve Louie and Jeff Neaton. And he was working on developing methods for investigating excited states in electronic structure. And of course, since 2015, Marco was at Caltech at the Department of Applied Physics and Material Science. And he leads one of the few groups who are focusing on actually developing new quantum mechanical first principles computational methods aimed at predicting and investigating electronic transport, as well as ultrafast dynamics and light matter interactions, focusing on realistic materials with these first principles approaches. And applications include electronics, optoelectronics, ultrafast spectroscopy, energy materials, and quantum technologies. So Marco has received a number of awards, an SF Career Award, the Air Force Young Investigator Award, and also notably the Psyche Volker Heine Young Investigator Award for electronic structure calculations. So with this, let us welcome Marco, and he will be presenting his work on novel first principles tools for electron dynamics in quantum materials. All right, Marco, it's all yours. Thank you.
Okay. Thank you so much, Boris, for the introduction and for kindly inviting me to give this talk. So today I will talk about new first principles computational methods to study electron dynamics in quantum materials. Now, as you know, materials are becoming increasingly complex, and we have examples of that in various fields. In electronics, for example, it's now possible to make efficient transistors and power cables based on complex transition metal oxides. For example, this is a transistor based on strontium titanate, and this is a power cable based on an oxide high temperature superconductor. Another example are topological materials, in particular topological semimetals, which have emergent relativistic electronic dispersions. And now with these materials, it's also possible to make electronic devices. Now, these two classes of materials, complex transition metal oxides and topological semimetals, are two examples of complex quantum materials that are envisioned for the next generation of electronic devices. Now, it's clear that these materials have structures and interactions that are far more complex than the simple semiconductors and metals like silicon and copper are currently used for these technologies. And so the challenge for theory then is to develop accurate calculations that can capture how electrons interact and move inside these materials, and then ultimately, with this knowledge, aid the design of this next generation of devices. Now, this challenge for theory can be tackled by leveraging advances in computational materials theory. In particular, today I will talk about so-called first principles methods, which use the structure of the material as the only input. And without using any free parameters in the theory or any information from experiment, they aim to make quantitatively accurate predictions. Now, the workhorse in this field is density functional theory, which can be used to investigate bonding and the ground state properties in materials with a good trade-off between accuracy and computational cost. As I will show you today, building on top of density functional theory, it's now possible to compute the interactions of electrons in materials. For example, the interactions between electrons and atomic vibrations, so-called phonons, or the interactions with defects. And then using these interactions, then we can make more precise models of electron transport and dynamics. Now, besides advances in the methods and software, there's also significant advances in the hardware, where now we're able to run these calculations on highly efficient computers. And so due to a combination of all these advances, it's really a great time to investigate electron dynamics in materials using first principles theories. This is the topic that is really at the center of my scientific interests. And I work on several aspects of it, but today I've decided to focus on just one, which is developing a framework to accurately compute electrical transport properties in materials, such as the conductivity and the carrier mobility, which is the conductivity divided by the electron density, and the mobility is a key figure of merit for materials employed in various devices. The novelty again here is that these calculations use the structure of the material as the only input. I will show you today that with these first principles techniques, we can predict the transport properties, for example, the mobility as a function of temperature and doping with a high accuracy in various families of materials. But we can also shed light on the microscopic mechanisms that govern transport and ultimately use this knowledge to help the design of new materials. Now, a key advance for these studies is the ability to accurately compute the interaction between electrons and atomic vibrations, phonons. These electron-phonon interactions control transport near room temperature and over a wide temperature range. Now, the idea here is that as the atoms move, they perturb the potential seen by the electrons. And as a result, the electrons are scattered, for example, in a solid from an initial electronic state with a certain band N and crystal momentum K into a final state by absorbing or emitting a phonon. The probability amplitude for each such scattering process is encoded in these electron-phonon coupling matrix elements, which are a central quantity in the theory. These coupling matrix elements are notoriously difficult to predict with analytical theories, where they're usually treated with crude approximations or even used as free parameters in the theory. However, using density functional theory and related methods, it's now possible to compute these scattering amplitudes with a high accuracy, and in particular, resolving them for different electronic states and phonon modes. And then we can use this knowledge, for example, to study the time scale of these scattering processes. This is the so-called relaxation time, which we can resolve for individual electronic states. And now we can use knowledge about both the scattering processes and the band structure, for example, here, the band velocities, to compute transport properties such as the conductivity and mobility as a function of temperature. And we can also change the doping by shifting the chemical potential. The simplest framework that I'll focus on here is the framework of the Boltzmann transport equation, in which the electrons are seen as wave packets that scatter through the phonons. The expression that I'm showing here is the so-called relaxation time approximation, but typically what we do is we actually solve the full linearized Boltzmann equation, which is a more accurate approach. So this framework is an excellent starting point to investigate transport in materials with weak electron-phonon coupling, and it's true in particular of many metals and semiconductors. My group has developed an entire open source code called Perturbo to carry out these calculations efficiently. In particular, starting from inputs from density functional theory, such as the electronic band structure and wave function, and from linear response DFT, from which we can obtain the phonon data. In Perturbo, we can efficiently farm these electron phonon matrix elements. And then, and this is the key challenge, we can interpolate them onto extremely fine grids in momentum space, which are needed to fully converge the scattering processes and the transport properties. The typical grids that are used are of order 100 by 100 by 100 or more points in the Brillouin zone. And so direct DFT calculations are out of the question. So the typical approach is to first transform these interactions onto a localized basis set, typically 1A functions. And then in this basis set, the interactions decay rapidly. Therefore, we can then Fourier transform them onto very fine grids for both the electron momenta K and the phonon momenta Q. And then typically by using billions or even more matrix elements, we can then compute transport properties, which will be the focus of my talk today, but also non-equilibrium dynamics, which is a topic I work on, but that I will not discuss today. To give you an idea of something that is easy to do now with Perturbo, but that was difficult until just a few years ago. In this framework, it's essentially possible to predict the resistivity in a simple metal like copper, silver, and gold at room temperature, or the mobility in a simple semiconductor like silicon. And with a calculation that takes only a few minutes, get a result within a few % of experiment. Now, the challenges, however, for real materials, both conventional and quantum materials, are related to several aspects that make them truly complex. In particular, real materials have polar bonds, and so the electron-phonon interactions can be long-ranged. They can have complex crystal structures. The electron-phonon coupling can be strong. Also, the electron interactions can be difficult to treat, and that's particularly the case for quantum materials. In particular, for systems with heavy atoms, spin-orbit coupling is important. And then for correlated materials with D or F localized electrons, one has to take into account the strong correlations. And finally, all materials have defects, which tend to govern transport at low temperature. So today, I will show you how in the last few years, we have tackled each of these challenges, and then each of them essentially require us to go beyond the simple framework that I've shown in the previous slide. And then by addressing these problems and making progress on them, we've now been able to make these first principles calculations of transport possible in much broader classes of conventional and quantum materials. So I will follow this order. And I will first focus on the fact that many materials have polar bonds. And for polar materials, as the ions vibrate, they generate long-range electron-phonon interactions, which can be grouped into a dipole and a quadrupole term. Now, the dipole is the well-known Froelich coupling with the longitudinal optical, or LO phonons. And the challenge to include it in the transport calculation, it's due to its divergence as 1/phonon weight vector, which essentially forces us to use extremely fine grids. In 2016, we developed a clever numerical approach to split the short and long-range interactions. And this approach has speeded up the calculations for polar materials by orders of magnitude. And using this advance, we've been able to show the first calculation of the mobility versus temperature in a polar material, gallium arsenide, done entirely from first principles. The computed mobility, which is shown here in red, as you can see, agrees with the experiments extremely well. But we can also shed light on the microscopic mechanisms. In particular, we predict that for an electron in the conduction band of gallium arsenide, it would take 168 femtoseconds to emit an allophonon, and that compares extremely well with the experimental time measured in a hot electron transistor of 165 femtoseconds. And so this work then established the accuracy of these calculations for both the macroscopic transport properties and the microscopic mechanisms that govern them. Recently, we have completed the first principles theory of long-range electron-phonon interactions by showing in these two works, in a collaboration with Cyrus Dreyer, how to properly include the quadruple term. We have shown that this quadruple term is important, is present in all materials, but it's particularly important in piezoelectric materials, so non-centrosymmetric ionic systems, like, for example, lead titanate or many complex oxides. And so we have shown that to correctly describe the coupling between the electrons and the acoustic modes in piezoelectric materials, it's truly important to include this quadruple term. So now this framework essentially allows us to study broad families of polar materials, and in particular complex oxides, which you could argue are the quintessential quantum material. So we're now focused on oxides. Oxides have many aspects that make them complex. Besides being polar, they also have structural phase transitions. For example, for the prototypical case of strontium titanate, this material is a cubic perovskite above 100 Kelvin, and it distorts to a tetragonal structure below this temperature. Now, the challenge for these materials with structural phase transitions is that the atomic vibrations that accompany the phase transitions, the so-called soft phonons, are notoriously difficult to describe from first principles. In particular, if you do a phonon calculation shown here on cubic strontium titanate, so you're typically interested in the high temperature phase, you see that the soft modes show up as dynamically unstable modes, which is unphysical. You see here they have these imaginary frequencies, which are shown as negative here. And so therefore, we're not able to quantify the coupling with the soft phonons and their effect on transport. Now, in 2018, we tackled this challenge in a collaboration with Ole Hellman, and we used an approach he has developed that is called a temperature-dependent effective potential. This approach is able to accurately compute phonons as a function of temperature. And you see here with this TDEP method, now all the phonon modes are stable, including the soft ones. Now, using these accurate phonons, now we can compute the electron-phonon coupling for all modes, including the soft ones. In cubic strontium titanate, we have established that the coupling with the LO modes is still the strongest, because this material is polar. However, the coupling with the soft modes is the second strongest. And now, using this knowledge, we've been able to solve an open puzzle in strontium titanate, which is the fact that experimentally, the mobility goes like temperature to the -3 over a wide temperature range in the cubic phase. The origin of this temperature trend has been heavily debated. Our calculation, shown here in blue, can capture this temperature trend extremely well. You see, we get T to the -3.12 versus 3.09 in experiment. And we've been able to show unambiguously that this temperature trend is due to a combination of scattering with the allophonons near room temperature and with the soft modes at lower temperatures. You see, if you don't include the soft modes, the temperature trend is entirely wrong. So this is an example of how these methods can truly shed light on the microscopic mechanisms. Now, as you see here, our calculation, which is based on the Boltzmann transport equation, gives a mobility that is still an order of magnitude greater than experiment. The reason for that is related to the fact that in many oxides, the electron phonon interactions are stronger than what one can compute using lowest order perturbation theory, which is the approach that we have used so far in this talk. In particular, in the presence of strong coupling between the electrons and the lattice, the carriers form polarons, which are electrons strongly coupled with the lattice, that as they move, they carry the lattice distortion with them. So the challenge now is how do you include these strong electron phonon interactions and polaron effects in the first principles framework? To address this problem, we have developed a so-called finite temperature cumulant approach. I will not get into technical details, but the main idea, which is outlined here, is that we use an exponential ansatz for the Green's function. And now we put the electron phonon interactions in this exponent, which is called cumulant. Now, without really knowing the technical details, you can imagine that if you now Taylor expand this exponent, you're going to get all sorts of higher order electron phonon processes. And therefore, the Green's function is hopefully going to be able to capture these polaron effects. To show you this, from the Green's function, we can obtain the electron spectral function for an electronic state in cubic strontium titanate near the bottom of the conduction band. Now, the electron spectral function is essentially the density of states for one electron, and therefore we would expect to see a peak in this function at the band energy, which is set here to the 0. This is the so-called quasi-particle peak. However, due to the presence of the strong coupling with the allophonons, now in strontium titanate, we find these two satellites in the spectral function, which are a hallmark of polaron effects. In particular, you see the strongest satellite, which is spaced by the band energy, by the energy of the allophonon, which is about 100 millielectron volts. This is the most pronounced satellite. We realized that it has been observed in high resolution photoemission experiments, which have shown, as you see here, that about 100 millielectron volts, as predicted here, below the conduction band, there is a pronounced satellite. So this is a major success for the theory, essentially establishes that these electron spectral functions are accurate. And now, equipped with these accurate spectral functions, we have developed fully quantum mechanical calculations of the transport properties using the framework of Green-Kubo theory. Now, in this framework, the conductivity and mobility are obtained directly from the spectral function using this formula, and therefore they include polaron effects. Using this level of theory, which goes beyond the simple particle scattering picture of the Boltzmann equation, we've now recomputed the mobility in strontium titanate. The result shown here in red in this level of theory, which I'm calling cumulant plus Kubo, show that now when we include the polaron effects, we can accurately capture both the temperature dependent and the absolute value of the mobility, which is now predicted within a factor of 2 of experiment over a wide temperature range. So this level of accuracy for a calculation that uses no free parameters on a complex oxide with polaron effects is entirely unprecedented. And so on one hand, this method sets the stage for studying broad families of oxides and materials with polar effects. It has also allowed us to dig deeper on the physics of strontium titanate. In particular, if we compute the spectral functions for all the electronic states, you see now the quasi-particle peaks shown here essentially show the renormalized conduction bands. And at higher energy, you have the satellites. Now, if we plot the integrand of the conductivity formula, we see that at low temperature, the main contributions are still from the quasi-particle peaks. So it's still the picture of the electrons that scatter, although now these are renormalized quasi-particles, both in mass and in spectral weight, which is about half of the normal spectral weight, because half is lost to the satellites. However, at room temperature, and as you increase temperature, essentially we find a higher and higher weight. At room temperature, the weight in particular contributed by the satellites is about half of the total conductivity. And so these regimes where the satellites and the essentially the polar effects are contributing strongly goes beyond the simple picture of electron scattering. To show this result more clearly, we have computed the optical conductivity in strontium titanate. You see here at low temperature, it's a peaked Drude function, and then it broadens at higher temperatures. And then using an approach developed in this work, from the optical conductivity, now we can extract an effective scattering rate. This is no longer lowest order perturbation theory, so we don't have a scattering rate, but we can still extract it from the optical conductivity. If we plot the scattering rates multiplied by h bar, so in energy units, you see here that it increases rapidly as a function of temperature. Now, for a transport regime, where you view transport as due to particles that undergo discrete inelastic scattering processes, there's a limit for the scattering rate. In particular, the product of the scattering timescale tau with the typical energy loss, which for phonon scattering is of order kT, in quantum mechanics has to be greater than h bar. Therefore, when you write the scattering rate in energy units, the result, if this picture is to hold, has to be smaller than kT. This is the so-called Planckian limit of transport. What we find in strontium titanate, to our surprise, is that at low temperature, transport is below the Planckian limit, and so the particle scattering picture holds. However, as you increase the temperature and already at room temperature in this well-known system, strontium titanate, actually transport goes beyond the Planckian limit, and this is a signature of the strong interactions and polar effects. Now, as you know, this idea of the Planckian limit and Planckian transport is kind of a hot topic in many correlated quantum materials currently. And so these tools equip us to study transport in some of those systems, particularly at high temperature, and hopefully shed light on this Planckian limit transport. On a more practical level, for people who are interested in designing new materials, these tools now allow us to study transport ranging from band transport, so weak coupling, to the polar regime. In this work, we have studied about a dozen perovskite oxides, looking for trends for high mobility oxides. So how would you design basically an oxide with a high mobility? What we found consistently is that systems like strontium titanate and potassium tantalate that have a d orbital character in the conduction band tend to exhibit strong polar effects, and therefore their mobility is lower, and one needs the accumulant approach to correctly describe transport. However, in systems like barium stannate and strontium stannate, which have an S-like conduction band, we found that in general, polar ion effects are weaker, and these materials have a higher mobility, and they can be described with the simpler Boltzmann theory. So this study now allows us to find a descriptor for high mobility oxides. So look for an S-like conduction band. And you can actually deduce this band character just by looking at the formula for these compounds. And so without even doing transport calculations, you might be able to discover high mobility oxides, for example, in the framework of database searches of materials. For example, that's the topic that Professor Boris Kaczynski focuses on. And so these tools try to lay the foundations for these studies. Okay, I will now come to a central topic for quantum materials, which is the electronic interactions. Now, many materials, but in particular topological materials, have heavy elements which have a strong coupling between the spin and orbital degree of freedom. Now, this spin-orbit coupling can already be included in the electron phonon coupling matrix elements within density functional theory. The challenge, however, is that these calculations with spin-orbit coupling, because they're typically expensive, they're usually done only in a small portion of the Brillouin zone. And then the matrix elements need to be rotated to the rest of the Brillouin zone. We have shown in our Perturbo code paper that our code Perturbo can carry out these rotations accurately, in all cases matching the density functional perturbation theory benchmark. Now, to our surprise, when we tested the other main open source code used to compute electron phonon coupling and transport, this code is called EPW, we found that this code actually makes very large errors in the presence of spin-orbit coupling. And the reason is essentially they have failed to correctly rotate the spinor. And so the conclusion now is that Perturbo is quite unique in its ability to compute electron phonon coupling in the presence of spin-orbit coupling and then efficiently interpolate these matrix elements and use them for transport. This allows us to do a couple of things. One is we have started investigating spin relaxation for now in semiconductors using first principles calculations. So the idea is that in a simple centrosymmetric semiconductor like silicon, where the bands are twofold degenerate, in the presence of spin-orbit coupling, the main mechanism, for example, if you inject spin-up electrons in the material, for the spin to decohere and flip, is actually this spin flip processes mediated by phonons, which are possible only due to the spin-orbit coupling. This is the so-called Elliott-DFA mechanism. In silicon and in diamond, which we also studied in this work, this is the dominant process for spin decoherence. And so in this work, we've been able to compute these spin flip matrix elements, which are 1,000,000 times weaker than the normal spin conserving matrix elements. So the energy scale is order nano electron volts. But we can still compute them accurately. And then combining, again, millions of them, for the first time, we have computed the spin relaxation time in a semiconductor entirely from first principles, so without using any free parameters in the theory. You see the result of this calculation shown here with the solid line is in extremely good agreement with experiment. And in the work, although I will not discuss it here, we've also shed light on the mechanisms that lead to the T-cube dependence of the spin relaxation time, and also showed how the spin flip and spin conserving scattering processes differ. Now, using this tool, we're now extending it to include other spin scattering mechanisms. And then with these new tools, we're now investigating decoherence in spin qubits and also spin decoherence in materials for spintronics. Now, more importantly, also from a method viewpoint, this calculation validates our implementation of the spin-orbit coupling, because this effect, the spin decoherence, is entirely driven by the spin-orbit coupling. So we're confident that we have the right approach, and we can investigate a wide range of materials where spin-orbit coupling is strong. So recently, we started investigating topological semimetals, in particular this system, sodium bismuthate, which is a Dirac semimetal. This material is sort of unstable in air, and so it has mainly been measured at low temperature. But now with the computational tools, we can actually make predictions up to higher temperatures. In sodium bismuthate, first of all, what we found is that there is a very strong band renormalization compared to the DFT calculation. So this is basically a moderately correlated system. And using GW, we have obtained band structures that match ARPI's experiments very accurately. And so confident of our band structure accuracy, now we have predicted that in this material, for electron carriers over a wide temperature range, the mobility at room temperature is as high as about 100,000 centimeters square per volt second. So to give you an idea, that's about half the value as suspended graphene. However, in this case, this is found in a bulk system, a bulk crystal at room temperature. The other thing that's very interesting that mainly comes from this large band renormalization is that there is a strong asymmetry between the electron and hole transport, which is obviously different from graphene, where there is this electron hole symmetry. In particular, in sodium bismuthate, we predicted for holes, the mobility is going to be an order of magnitude smaller than for electrons. And so this is to show you now that these calculations are starting to be able to tackle these more complex topological quantum materials. The second aspect of quantum materials that I wanted to show you are so-called correlated systems. In particular, there are many transition metal oxides where electrons occupy highly localized D or F electronic states. It is well known that density functional theory typically over-delocalizes electrons in these localized states due to self-interaction error due to the incorrect account of exchange. But so the challenge here is that electrons in these localized states interact strongly via Coulomb repulsion. Obviously, these correlated materials are some of the most intriguing systems. They include mud insulators, cuprates, and other high TC superconductors, multiferroids, and so on. So the challenge is that in most of these materials, actually density functional theory fails to describe the ground state. Now, there are two key methods to compute the ground state of correlated systems. One of them is the Hubbard-U extension of density functional theory, so-called DFT plus U. The other one is dynamical mean field theory. However, calculations of electron-phonon interactions are currently not possible with either of these methods. So we've taken a first step in describing transport properties in correlated systems in this recent work, where in a collaboration with Nicola Marzari, we have developed electron-phonon calculations in correlated systems in the framework of density functional theory plus U. Now, to focus on a case study that we show in this work, we focus on this mud insulator, cobalt oxide, which in density functional theory is predicted to be an unstable metal. DFT usually cannot describe mud insulators very well. If you add the Hubbard-U term, which now turns on the local repulsion at the cobalt atoms, a DFT plus U can correctly describe the ground state of this material to be an anti-ferromagnetic insulator. And you see in this level of theory now, all the phonon modes are stable. Now, using this knowledge, we have computed the electron-phonon coupling, both in DFT, shown here in blue, and in DFT plus U, shown in orange. Now, because density functional theory describes the system as a metal, you see here in density functional theory, one completely misses the long-range Froelich coupling due to the allophonons, which would have a 1/Q divergence. The other error in density functional theories, you see, it gives this artificial and spurious divergences in the electron-phonon coupling, which are due to these spurious soft modes in the theory. When we turn on the Hubbard-U interaction, however, in the curve shown here in orange, now we can correctly describe the long-range interactions and this Froelich divergence due to the allophonons, and now all the other couplings are finite. So now we can correctly describe the electron-phonon interactions in a correlated system, the mud insulator cobalt oxide, and we can even study polaron effects, again, using the accumulant method. Now we can study the spectral function and, for example, see these satellite peaks due to the allophonons. These polaron effects are entirely driven by the Froelich coupling, and so they will be completely missing in just plain DFT. And so this tool is essentially a first step toward being able to describe particularly correlated oxides, and we hope that we'll use it broadly in the coming years. The last topic that I wanted to describe, obviously, all materials have defects. So far, I focused mainly on phonon limited transport, which is the main mechanism at room temperature. However, we've also developed tools to investigate electron defect scattering. That's particularly important, for example, in oxides, which are usually heavily doped. And so the dopants have an effect even at high temperatures, but also to describe transport at low temperature, which is typically defect limited. Excuse me. Okay, so now in density functional theory, in principle, you have all the tools to form the electron defect matrix elements. You can basically do a calculation with a large supercell containing a defect, and then subtract the Conchamp potential from a pristine supercell, and now you obtain this electron defect perturbation potential. The wave functions, however, in the simplified approach, you would have to use the wave function for the large supercell, and those are extremely expensive and essentially impossible to handle. Working with my student Ite Lu a couple of years ago, we have reformulated the theory and wrote it entirely in terms of primitive cell wave functions. This has allowed us to speed up this calculation of electron defect matrix elements by orders of magnitude. And in this subsequent paper, we've also shown how we can interpolate these matrix elements using 1A functions. So essentially now we have retraced the progress of the last few years in electron phonon calculations and now translated it for electron defect calculations. For example, now, in a simple system like silicon, you can predict the residual mobility at low temperature due to specific defects. And you can actually have the microscopic insight to show that, for example, a same concentration of vacancies and interstitial defects lead to a residual mobility that differs by an order of magnitude. So you can use this tool as a spectroscopy, for example, to understand which defects are present in a material or to predict which defects need to be minimized to improve transport at low temperature. Just to show you briefly, these first works were for neutral defects. Treating charge defects includes some technical challenges that we have recently tackled, in particular, including the long-range couplings, very similar to the frolic problem in electron phonon. So now we can include this frolic coupling, including the random phase approximation screening in the material. And now it's possible for us to compute the effect of ionized dopants. So these are charge defects, which are the common source of scattering in heavily doped materials at room temperature. This calculation for phosphorus doped silicon combines electron phonon and electron defect scattering in the full solution of the Boltzmann equation, the curve shown here in red. And you see that now we're able to compute the electron mobility with a high accuracy, not only as a function of temperature, but also as a function of doping with this approach. What's interesting is that electron defect calculations have typically used an effective mass approach, where one uses analytic formulas that use the effective mass. Obviously, that framework is not suitable for materials that have multiple valleys or anisotropic band structures, but also in particular for systems like topological semimetals, which have linear dispersions, the effective mass model cannot be used. Our calculations, on the other hand, make no assumptions about the band structure, and therefore we're able to tackle all these cases and therefore study defect scattering processes and defect limited transport in broad families of conventional and quantum materials. Now, I've come to the end of my talk. I'm going to show just two more slides. One, I would like to highlight our development of Perturbo as an open source code to study electron interactions and dynamics from first principles. Using the current release of this code, one can compute electron phonon coupling, and also use this knowledge to study various transport properties and also ultra-fast dynamics, which is a topic we work on that I will not discuss today. We have released this code about a year ago, and we already have a large and rapidly growing community of users. We have over 250 users. We believe the users are liking the fact that this code is particularly user-friendly. It's also highly modular, so it's easy to add a new piece of physics on top of the existing tools. It's currently parallelized using MPI plus OpenMP, and so it scales favorably up to tens of thousands of cores. So we've been using it routinely in large clusters and supercomputers. And besides the high performance, the code has really unique capabilities. Besides the ones that we have released, we have many more, but there is one that I would like to highlight in my final slide, which is the fact that recently we've been able to also include the magnetic fields in transport. As you know, actually many measurements of transport properties, particularly in quantum materials, are done at low temperatures in magnetic fields. So recently we have included the magnetic field term in the Boltzmann equation. One of the key challenges computing this momentum space derivative. And now we can obtain the entire conductivity tensor as a function of magnetic field, and this allows us to study quantities like the magnetoresistance or the Hall mobility or the Hall ratio. In this very recent work, we've shown these calculations in a few simple cases like silicon gallium arsenide and graphene. You see here in silicon, both the magnetoresistance and the Hall mobility for N-type and P-type silicon can actually be computed accurately. In the same framework, we've also implemented the Berry curvature. So for example, for both wild semimetals And for Dirac semimetals in magnetic fields, and now we're also able to include the anomalous velocity term due to the Berry curvature. We believe this tool is going to be instrumental to study transport in topological quantum materials in the future. So with this, I would like to thank my research group, both the current and the former members. And in this talk, I hope that I've shown you a quantitative framework for more precise calculations of charge transport in the framework of first principles calculations. I've shown you that these methods can provide microscopic insight into the transport mechanisms. They can also help interpret transport experiments, inform efforts to design new materials. I've shown you that we can now study, thanks to these advances, various classes of conventional and quantum materials, and I have highlighted new frontiers such as magnetotransport and calculations in correlated and topological quantum materials. And I believe that these frontiers are going to keep our community busy for the next few years. With this, I would like to thank you so much again for being here today and for inviting me to give this talk. And I will be most happy to take questions. Thank you.
Well, thanks very much. It's very interesting work, and it's great that you can actually figure out how these things work. For people who would like to ask questions, please type it in to either the Q&A or the chat on the bottom of Zoom. I have to start out, I have a question. You were saying that you had a mechanism for going beyond the Planckian transport that is a way of sort of cheating Heisenberg's uncertainty principle. Can you tell me how that works, or give me an idea what's happening so that you can do that?
So yeah, basically what's happening is that the Planckian limit is really a limit for transport in the picture where you have a particle that scatters. So that picture is the picture of the Boltzmann transport equation. It works when the spectral function is peaked and there's only a small width. However, when you have a strong coupling, you see part of the spectral weight gets transferred to the satellites. And when the satellites come into play, it's essentially not just the renormalized quasi-particles. So they're still particles. They may be lost some spectral weight. Their mass has increased, but you can still describe transport with a Boltzmann equation with properly changed weights and effective masses. So in that regime, you still have a particle-based transport, and so you expect that the Planckian limit will have to be satisfied. When the satellites come into play, essentially the scattering picture no longer works. The Boltzmann equation no longer works, and that's basically the case here in strontium titanate at higher temperatures. And so this violation of the Planckian limit is kind of expected. It's basically a manifestation of the strong interactions. There is nothing unphysical. It's just that the picture is no longer that it's the particles that are scattering. You could basically view it as a collective motion of the electrons and phonons that now form the polarons.
Okay, I think I've done. Let's see, questions, please type them in Q&A and or chat. Well, Christian says, thank you, Marco, for an excellent presentation. So that's very nice.
Thank you, Christian. I'm glad you liked it.
Any last questions? Okay, well, if not, thanks very much. It's great to see that people can do this. This is the kind of thing I try to puzzle out without doing any calculations.
Oh, I think there's a person who has raised their hand. Jennifer Calder, maybe, and Gabriel Schneider. So there's maybe two questions.
Can you see that?
Yeah,
I can.
Q&A.
Okay, go ahead.
Do you want to read? Okay. So Jennifer says, isn't the difficulty including DFT and U corrections and EPH calculations a difficulty with the implementation of U?
Yeah.
Okay.
Yeah, so thank you. I
Right.
know where this is going. So yes, you have to have linear response DFT plus U as the starting point, and that's why we've done this work in collaboration with Nicola Marzari's group, who's been developing this density functional theory plus U in the linear response version. The problem is still that to interpolate the matrix elements and basically show this kind of plots or actually do transport calculations and also Polaron effects, you basically have to implement the interpolation of the matrix elements. So using just quantum espresso and the current version of DFT plus U, you basically not be able to get very far because you'll be able to include the coupling on just a few coarse grid points. So this required implementing new routines in our Perturbo code to basically interpolate not only the Consham term, but also the Hubbard U term.
Okay, there's another question for Yashang Wang. In the DFT and U treatment, how do you differentiate the derivative of the Consham energy and the Hubbard energy, question mark? Is the Hubbard U a fixed parameter?
So to the first question, you basically have both terms, and so you can study the effect of the two separately. The catch, obviously, is that you run the ground state DFT plus U, and actually we found that one of the main effects is not just that you have an extra term here, but that basically DFT plus U changes the density and the wave functions. And so essentially, the change in the wave function, and particularly addressing the delocalization error for the D states, plays a key role. We've shown in that paper, in this paper, that even once you take that into account, if you study the effect of just the Hubbard potential, which you can because you basically have the two terms, we see that the effect is particularly strong for the cobalt atom, and in particular for the spin channel that is open. So this is an antiferromagnetic system with two cobalt atoms in the unit cell. So basically each cobalt has one spin band that is entirely filled and the other one that's partially filled. For the partially filled spin channel of the two cobalt atoms, the effect of the Hubbard U term, basically this electron phonon perturbation of the Hubbard U potential, is as strong as the Consham term. And so if you did not include it, you would basically make a large error. The question whether you use a fixed parameter, you can use it as a fixed parameter. However, in this work, we have shown we have used the linear response approach to also compute U from first principles, which was developed by Matteo Coccoccioni, who's one of the authors of this work a few years ago. I believe actually the tools are present already in Quantum Espresso to do these linear response-based calculations of U. So in this level of theory, you can still claim that there's no free parameters because even the Hubbard term U is computed from first principles.
Okay, thank you. Any last question? Well, if not, thank you very much. I enjoyed your talk. Thanks so much.
Thank you so much. Thank you for inviting me, and all of you for being here today. Thank you.
Great.
Bye, thank you.
Bye. Bye-bye.
Bye-bye.